Good day, students. In this clip, we're going to be going over an example on integration involving the use of partial fractions. So let's go ahead and take a look at the question. So number one is to evaluate the following integral. Evaluate the indefinite integral of 9 over x to the 1/2 minus x to the 1/3 dx. Okay, and we are also given a hint, and the hint is we're to substitute u for x to the 1/6 first. Okay, all right, let's go ahead and do the problem. So first of all, I need to express these two as a common denominator of 6. This fractional exponents, I need to convert the denominators to 6 so I can factor out the numerators to get 1/6. Okay, so let's rewrite the integral. We have the indefinite integral of 9 over x to the 1/2 minus x to the 1/3 dx. Now the goal is to convert the denominators to 6. So in order to convert this to 6, I multiply by 3 top and bottom, and then in order to convert this to 6 in the denominator, I multiply by 2 top and bottom. Okay, so now this integral becomes the indefinite integral of 9 over x to the 3/6 minus x to the 2/6 dx. Okay, the reason I'm doing this again is I want to make the substitution possible. If I can get the denominator to be 6, I'll just factor out the numerators and then I can advance with the substitution. All right, so check this out. I can write this as an integral of 9 over, and I can factor out the numerator, which is 3, so I'm going to be left with x to the 1/6 times x to the 1/6 to the 3rd power, because 3 times 1/6 is 3 over 6. The same procedure here. What are you going to have here? You're going to have x to the 1/6 times 2, because 2 is in the numerator, and if I factor out that 2, I'll be left with a 1 in the parentheses. Okay, so that's why I made the denominator 6. Okay, now that we've accomplished that, now we're going to make a substitution. So this integral is going to become the integral. Now notice this 9 here, I can factor that out, so don't keep writing it over and over again. 9 factored out, you're going to be left with 1 over u to the 3rd minus u squared dx. Alright, so this is a new nice problem we're going to integrate. Now let's factor out the denominators. We're going to have, write it as 9 times the integral from 1 over u squared times u minus 1 dx. Now we're going to decompose this integrand into partial fractions, okay, using the partial fractions decomposition algorithm. So let's decompose the integrand. Decompose the integrand. All right. Okay, so to do that, we're gonna, let's just say, focus on the integrand alone. Okay, so 1 over u squared times u minus 1 can be written as a over u squared, a over u squared first, a over u squared plus b over u, this is the decomposition of the first part, and then plus the other denominators u minus 1, we can just put a c there, c over u minus 1. Okay, all right, so there you have it. Okay, so now what we're going to do next is multiply both sides by the LCD. The LCD is u squared times u minus 1. So you basically multiply by u squared times u minus 1, both sides. So let's go ahead and do that. So if I multiply this side by u squared times u minus 1, and this entire piece right here, I'll multiply the numerator by u squared times u minus 1. Okay? All right, when I do that, on the left side, I'm just left with 1. On the right side, this u squared cancels with that u squared, so I'll have a times u minus 1 plus, and in the middle term, this u cancels out with one of the u's in the u squared, so I'll be left with b times u, and if I distribute that u to u minus 1, it's going to be times u squared minus u. And then the c, the u minus 1's cancel out, so you're just left with c u squared. Okay? Now, if you look at this, if I could solve for c here by simply setting c to 1. I mean by setting u to 1. If I set u to 1, this becomes a 0, it eliminates b. This becomes a 0, it eliminates a, and I can find out what c is, okay? So let's set u to 1 to find c. Okay? Alright, now to do that, we're going to have 1 equals a times u is 1, 0, I'm sorry. U is 1, so it's going to be 1 minus 1. 1 minus 1 plus b times 1 square minus 1 plus c times 1 square. Okay? So if we simplify that, we're going to get 1. This whole thing becomes 0. And then this whole becomes 0 here, plus c. So we can clearly see that c equals 1. Okay, so let's substitute this back into this equation that we have up here. And then we're going to expand it completely and then use the powers of u to set up equations, okay? All right, so now we have 1 equals a times u minus 1 plus b times u squared minus u. C is now 1. It's substituted there, so it's going to be 1 times u squared. Okay, so let's go ahead and distribute this completely and then use the powers of u to set up equations, all right? So here I'm going to have 1 equals, distribute, we have au minus a plus bu squared minus bu plus u squared. Okay? All right, now we know the highest degree here is u, right? I'm sorry, square, u squared, so I'm going to write this one as 0u squared. Since this is just a constant, plus 0u plus a constant 1. And let's go ahead and organize this using the squares first. So we have, what do we have here? Bu squared plus u squared. Okay. And then for the first degree term with the u, we have au minus bu. And then what do we have? Minus a. Okay. All right, let's factor it, and then we'll equate terms with like degrees to determine to set up our equations. Okay, so we still have 0u squared here plus 0u plus 1 equals let's see, we take out a u squared, b plus 1 plus, here we can factor out a u times a minus b minus a. Okay? Alright, so taking a look at this equation, we can equate the squares. Because this is u squared and this is u squared, we know that 0 has to be equal to b plus 1. So we know that b plus 1 equals 0. Okay? Because these are see this square? This term and this term, we set them equal to each other. Alright? Cancel out the u squared, and then you have 0 is equal to b plus 1, because those are the squares. Subtract 1 from both sides, you have b equals negative 1. Alright? The two ways you can find a, see this constant right here is equal to that. So we have, you can do negative a equals 1. Divide both sides by negative 1, you have a equals negative 1. Alright? Another way you can do it is you can use this second equation right here, this piece, the first degree term and the first degree term here. You go, since the u's are equivalent, you just have a minus b equals 0. But wait, we know that b is negative 1, right? So if I put it here, I have a minus negative 1 equals 0. So we have, what do we have? We have c. We have a plus 1 equals 0, hence a equals negative 1. That's another way, a longer way of finding a. Okay, so we know what our three constants are. We know that a is negative 1, b is -1, c equals 1. So these will help me decompose that original fraction I had. All right. So let's rewrite it. So now 9 times the indefinite integral of 1 over u squared times u minus 1. The u can be decomposed into 9 times, how did I set it up here? Let's go up a little bit. Okay, there you have it. So I did ABC. Okay, so let's do it that way. ABC. So a is -1, so it's um, negative 1 over u squared, because a is -1, minus b is also -1 also, so -1 over u, and then plus 1 over u minus 1 for the c. Okay, du. All right, let's go ahead and evaluate this integral. I'm going to do this using term-by-term integration. Okay, so let's not forget the 9 that we have out there. So here this is going to become 9 times the indefinite integral of -1 over u squared du plus the antiderivative of -1 over u du plus the antiderivative of 1 over u minus 1 du. Okay, this term-by-term integration here. All right, so let's do the first one. Let's integrate the first one. This is -1 over u, so I can rewrite this as, let's rewrite this as the integral of, can factor out the negative, u to the -2 du, makes it easier to integrate like that, and then minus, pick out this minus, the antiderivative of 1 over u is the natural logarithm of the absolute value of u, plus this one, for this one we can use the u substitution here. If you use we can use a v substitution, so to speak. So in this integral, I'm going to do it on the side here, okay? Let's do it on the side right here. So for this one, I'm going to say let v equals u minus 1. Okay, this is a composite function. It's a composition of a linear function and a rational function. Okay, if you differentiate the inner function with the linear function, you end up with a product of the other function, which is just a constant function 1. All right, so if v is u minus 1, dv is going to be du. Okay, you see that? So if we make the substitution, here, this integral can be rewritten as the antiderivative of 1 over v dv. You see that? 1 over v dv. All right, and then you notice it looks like this other one we have right here. So let's go ahead and continue with our integration. So in the first piece right here, we're going to have 9 times negative. If we use the power for integration here, we're going to have u to the -1 over -1. You just add 1 to the power, and then the same thing with the denominator, like that, minus the natural logarithm of the absolute value of u, plus the antiderivative of that is simply going to be natural logarithm of absolute value of v, like that, plus it, plus a constant c. All right, let's simplify this a little bit further. This becomes 9 times, using the reciprocal property of exponents, as u goes down and minus these two signs, you have negative positive, so you have 1 over u minus the natural logarithm of the absolute value of u plus, remember what v was, right? What did we say v to be? We said v should be u minus 1, so let's put it back. Natural logarithm of u minus 1 goes there plus c. Okay? All right, now we're not done yet. Remember, in the starting part of this problem, we made a substitution, right? We said let u be x to the 1/6. Now we have to put it back as it was. All right. Well, before I do that, how about we use some properties of exponents of logarithms here to condense our expression real quick. So I can, well, let me make the substitution first before I simplify that. So we can rewrite this as 9 times 1. Let me do natural logarithm. I'm just reordering terms here. Natural logarithm of x to the 1/6 minus 1. That's this last term right here. Minus the natural logarithm of x to the 1/6 plus 1 over u. Oh, snap. So we already said that we want to put it back as it was. So instead of u, I'm going to use x to the 1/6. Okay, and that whole business plus c. All right. We don't even need the absolute value bars because we know that if you raise something to the 1/6, there's no way it's going to be, it's going to work out nicely. So the 6th root is always positive, except it's unreal. If you take the 6th root of a negative number, you have an imaginary output. Okay, so we did set up like this. All right, so we can write our final answer as 9 times natural logarithm of x to the 1/6 minus 1 minus natural logarithm of x to the 1/6 plus 1 over x to the 1/6, that whole thing plus c. Or we can also rewrite this. If we want to use the properties of logarithm, we can condense these two expressions. We're going to have 9 times the natural logarithm of x to the 1/6 minus 1 over x to the 1/6, and then that whole thing plus 1 over x to the 1/6. All right, and then this whole expression plus c, and then that's basically that. All right, so there goes the two forms of your solution. So thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel by clicking up here, and please post the comments to let me know what you think about this presentation. And more clips come from microsoft.com. Thanks again and have a wonderful day.